Been clear based on the reading, but today we're going to kind of focus on how we know other galaxies exist. So before we get into talking about other galaxies, we should actually understand how we learned that there are other galaxies, and then also talk a little bit about how we know where we are within our own Milky Way. And so kind of to do this, we're going to structure it a little bit around the science that was going on during what was called the Great Debate, which was the Shapley versus Curtis debate about whether or not spiral nebulae were other galaxies or within our own Milky Way, and then also about where the sun is centered inside of the Milky Way. So I want to just start by just taking a little bit of time to work in breakout rooms, because that seems to be good, to just kind of talk about two things, like what maybe stood out. Was there anything that surprised you about the Great Debate and what they were discussing, what was known then and what wasn't known back in 1920, which is only 100 years ago, which is kind of crazy. And then also, if your team, your group, so there's two questions, sorry. Question number one, what surprised you? Question number two, if you wanted to figure out what the island universes were, what the spiral nebulae were, what would you try to do? What data would you look for, maybe with or without the limitations they had then? So I will kind of wander between the rooms. I think this will be maybe 10 minutes to discuss those 2 points. We're just waiting on one group to rejoin. I always feel a little weird with the breakout rooms because I can't walk around and see how people are doing. I just kind of guess. But I think it's better than, whatever else. Okay. Everyone is back. So how about, I'm gonna just breakout room 2, which for me was Aaron, Haley, Jess, Thomas, and Zane. Can one of you share your plan for how we might determine what spiral nebula are?
Well, go for it.
You can go, Tom.
I guess we just talked about like Cepheid variables, since I guess on the website about the debate, they said like they had already figured out about Cepheid variables. They just weren't like sure of the validity. So I guess our main way was like, okay, we'll just check distance with Cepheid variables, and if it's like heinously far away, then you can probably guess. Or especially if it's like much further away than all the stars in the Milky Way, you can kind of guess that it's not part of the Milky Way itself.
Nice, okay, so I think that's semi-similar to the groups I talked to. Does anyone else want to add anything from one of the other groups? Yeah, the big idea, I guess, similar to what Shapley and Curtis were both doing, is if we can figure out the distance to these things and compare it to how big we think the Milky Way is, then maybe we can figure out whether or not they're other galaxies or they're within our own galaxy. And that's kind of the point that a lot of this debate in air quotes, was it actually debate? Who knows? It's always called the Great Debate though, so we throw it in there. But what it was about. So I'm just going to go through a few of the arguments. So kind of similar, one way that Shapley argued that we couldn't, we were not in, these galaxies were inside, was based on Van Manen's measurements of rotation speeds. So the argument here is if you can measure a rotation speed, you can kind of get an idea of mass, since gravity controls orbits, so there's some iffiness because they don't know about dark matter yet, but you can get an idea of mass if you can measure rotational speed. If you can find mass, you can kind of try to figure out how bright it would need to, or nope, this is later, sorry, I misspoke. Let me rewind. If you can measure an angular rotation speed, you can use that angular rotation speed to try to figure out how far away it might be based on, okay, if we're going to translate this into a physical speed, what are those angles to try to, how far away does this need to be to get a speed that makes sense in terms of translating angles to actual numbers. So we were measuring rotation speeds in arc seconds. If we wanted arc seconds per year, if we want to change that to parsecs per year, we can use trig to like convert that if we know the distance. So they can find the distance based on the rotation speed. Sorry, I'm getting ahead of myself. The problem was, and so based on the measurements that Van Manen did, they thought that M101, which is the galaxy pictured here, was rotating way too fast to be inside of our galaxy. Sorry, I'm trying to. Okay. So if it was the same size as the Milky Way in diameter, it would need to have a rotation speed of 5,000 kilometers per second, which is about 1% the speed of light, which seems ridiculous. So the problem was, what Van Manen was measuring, we don't really know. It wasn't the rotation of this galaxy. With face-on galaxies, you're not going to be able to actually see rotation. So he was seeing stars moving that weren't actually moving. So the science behind it was right, the measurements were incorrect. So we were getting ideas that galaxies must be, these spiral nebulae must be really close and therefore must be small in order to explain the motions that Van Manen was seeing. So rotation speeds, to get them the right order of magnitude, we needed these spiral nebula to be close and within the Milky Way. So that was kind of Shapley's first argument, that spiral nebula must be inside of the Milky Way. Does that make sense? Any questions? So that was one of the points that they were incorrect about. And Curtis kind of thought these measurements have to be wrong, so that doesn't matter, which Curtis was right on that point. Okay. The other thing that happened in this debate that was kind of fun was that they also discussed moving the center of the universe. So I think some of you talked about this a little bit in your breakout rooms, but one of the points of the debate was about where spiral nebulae were, and the other was, where is the sun within the Milky Way? And Shapley was arguing it was in the disk, it was not in the center, it was somewhere out in the arms of the Milky Way, whereas Curtis thought it was the center of the Milky Way, and all the stars were rotating around it. The entire Milky Way was bound to, and that kind of put the center of the universe at the sun. Curtis was saying the center of the universe is about, I think he said 10 kiloparsecs over that away, where Sagittarius A star is. And so I threw this in because I thought it was silly, but just this idea.
Philosophers and astronomers have searched for it for centuries, but many Tulsans already know the center of the universe is right here in the shadow of downtown's tallest building. Storm Show meteorologist Kirsten Horn reveals the mysteries of a Tulsa must-see.
It is one of Tulsa's most fascinating and well-known phenomenon, the center of the universe, a landmark that stumps an estimated 10,000 visitors from across the country each year.
It's basically a focusing anomaly. You're standing in the middle of a circle that's caused by concrete benches.
It doesn't matter which direction you face or how loud you are. When you talk, your voice will hit these concrete walls around you, reverberate back, and create an echo that we know as the center of the universe.
So maybe the center of the universe is in Tulsa, maybe it's at the sun, maybe it's at Sagittarius A star, but we're kind of, throughout time, we're kind of moving the center of the universe. So like today I talked about in 110, there was geocentric model, Earth is the center, heliocentric model, sun is the center. Now Shapley is proposing that maybe there's something else even that's the center of the universe. So I thought this is also kind of just a fun thing to think about. So I'm gonna open up our breakout rooms again in a second, and I'll do something similar where I'll pick on one group to share, but just how does moving humans out of the center of the universe and potentially back, with now there's not a center of the universe, so yeah. But how does that what does that tell us about science and humanity, like how people interact with science and how we think of ourselves throughout time? So let's maybe take 5 minutes to discuss about this in our groups, and then we'll come back together. Cool, looks like everyone's back. Does anyone, I'll just kind of open this. Does anyone, I know this is a bit of a fuzzy question, but was there anything that got brought up in the groups that people are willing to share?
I thought it was pretty interesting how, like, I guess it would be before like the 1900 kind of debate, but when you're thinking like geocentric, heliocentric, that kind of stuff, how like religion affected the debates and how that's like non-existent now.
Yes, maybe it's like, it's still, I'm gonna push back just because I think there is still like creationism and talking about, it's like, it's there in a different way, like
Okay, I see.
centering around humanity, but yeah, we're okay with the earth not being the center, but we're not okay with dinosaurs or something. I don't know. Yeah, it's interesting how
something that we kind of built off after you came into our room, Jessica, was that like decentering ourselves helps us sort of develop a sense of empathy also, by growing, by studying things that aren't directly affecting humanity. We like grow our sense of understanding and appreciation for the things that are going on around us, not only in like on Earth, but also in the universe at large.
I think that's beautiful. I really like that, like when we think of, you know, basic science and how it's important to humanity as just, you know, changing the way we see ourselves and changing the way we see the world. And, you know, not every part of science has to be, I'm going to make the next rocket ship or I'm going to find a cure for cancer, but just understanding our planet is an important thing that science can help us do, and our universe. Anything else? Well, thank you all for engaging me on that. This is something I'm really interested in. I think it's fun to think about how science and humanity kind of, or science and just the ways we think about ourselves kind of change over time. Okay. So there were, like we kind of mentioned throughout this lecture, there were kind of two parts of this debate, both what the spiral nebula were and then also where we are within the Milky Way. So I guess even just like thinking about when you go outside, if you're not even using a telescope, how do we realize that we're in a disk and not necessarily in a sphere? If we can't take a picture, my bad joke, it's like doesn't work as well anymore, but we don't have a selfie stick long enough to take a picture of the Milky Way. You know, Voyager's going for it, but it's going to take millions and millions of years for Voyager to get out of the Milky Way since it's taken so long to get out of the solar system. So we need to understand what the Milky Way looks like without leaving it. So it's like kind of the hard part about figuring out where we are. But even in this discussion, they kind of knew that it was a disk. So where do we get that idea from?
I would think that it would be from just looking up at the sky. You can see the denser part of the sky and basically just a line that goes all the way across. So
yeah, so you can imagine, yeah, if you were, you know, inside of a pizza and you looked out somehow, there would be some places where it'd be very hard to see and some places where maybe it'd be more open. So you could say like, I am in a pizza. And that's kind of what you're able to do with the Milky Way. And that was the initial thing that William Herschel did. was he would go through and he would count stars and try to make really detailed maps based on the locations of the stars to figure out the shape of our island universe, our galaxy, what we were in. And this was, again, knowing that it was a flat disk, so kind of an idea that we are this flat disk. The sun is kind of right here. So there's one darker thing, but it looks pretty uniform no matter which direction you look. So this was kind of the initial idea, was that if you just go through and you count stars and you try to figure out how many are in every direction around us in the disk, it seems to be that we are probably in the center because there are equal numbers of stars no matter which direction you look-ish. That's not quite right. Obviously, we know we're not in the center now. So why do we think, what's the problem with this? Why doesn't this work? What else is in the galaxy?
Dust and stuff that blocks light from farther stars.
Yep. So that's basically the problem, is that William Herschel did not take into account the fact that there is dust in our galaxy. So the way that a lot of us maybe have interacted with dust that kind of makes more sense is, unfortunately, if there's a fire, which there are more and more of now, if you look at the sun will look redder as it passes through smoke. Same thing happens with dust in our galaxy. It's similar in size actually to smoke, so it's a pretty good kind of comparison. So it reddens the light from stars, it blocks and absorbs light from stars. So if you look in a direction where there happens to be dust, it looks like there aren't very many stars there, when there could be quite a few. We're just not seeing them because we're not seeing the light from the dust. So this is a map. We'll talk about this more next week or 2 weeks from now, I think. I'm working on that activity, so hopefully it'll be fun. But if we look in the infrared, that's a way to measure the dust in our galaxy, because dust is warm and it emits kind of a black body, a Wien curve kind of thing. So if we look at the temperature that that dust is, we can map the dust in our galaxy and we see there is quite a lot. And that causes issues if you just want to count stars. So Herschel, again, was doing science right, and he was working with the best knowledge he had. It just, his method was flawed because he didn't realize how much dust was in our galaxy, and they didn't know at that point of time there was a lot of dust in our galaxy. We don't have infrared telescopes back in, early 1900s. So if he had accounted for dust, maybe he could have gotten this right, but he wasn't. So instead, a way to get the idea of where we are in our galaxy is instead to use the positions of globular clusters. So I guess if we think about globular clusters, why are we not going to run into the same problem? This might be getting a little ahead, but.
Is it just because they're like so bright that even if they do get reddened, like we can still see them pretty well?
So that's part of it, but it's going to be also, Sabrina.
They're not in the disk of the galaxy.
Yeah.
So there's dust.
Yeah. So we'll talk about this a little bit more later as well, but globular clusters aren't in the disk, they're going to be more in the halo. So if we assume that globular clusters are evenly distributed throughout the halo of our galaxy, we can kind of try to map them out and see what the distribution is and use that to figure out where we are in relationship to the center. So same idea, we're going to use the distribution of globular clusters to figure out where the center is and where we are within that center. Okay. I wanted to pause here just as another quick kind of review of other things, because I won't talk about this much. I think Nathaniel told me that you guys did some isochrone fitting before. Can someone give me just a quick overview? Does that sound familiar?
We did it in astrocomputing.
So
what?
Go for it, Ethan. what?
Okay, so as you can see from these beautiful diagrams, there is, like, you can age a galaxy based on this turnoff point from the main sequence, because the larger stars, which are going to appear towards the top left of these of the sequence, are going to burn up faster and move off of the main sequence, and there's an association of that turn off with age, because if we know how big they are, we know when to expect them to get off of the main sequence. So if we take a big giant survey of a bunch of stars and fit them to with isochrome fitting, you'll be able to like see this pattern occur where the bigger stars are turning off of the main sequence, and we know how old that is. Like, depending on where the turnoff point is along that main sequence, we know what age is associated with that position.
Perfect. Yeah, so this is often used, I threw this in here because this is often used with globular clusters. Since we assume globular clusters, all the stars are going to be approximately the same age. It doesn't usually work with galaxies because we don't assume that all the stars in a galaxy are going to be the same age. But with globular clusters, there's a good chance they are. So if you can find that turnoff, we know that, you know, A stars will burn hydrogen on the main sequence for approximately 10 billion, certain number of times. I don't remember, sorry, should look that up. But if we see that the A stars are still on the main sequence, we know that the cluster must be this old, but the B stars have moved off. It must be between these two ages. So you can kind of work out your age of your cluster based on which stars are on the main sequence and which aren't. And we can fit an isochrone, which is just a line on your HR diagram that fits that age. So isochrone, I think, is like chronos, time, age, iso, all the same, I think, isometric, all the same. So all the same age, we can fit that. So exactly what Ethan said, but just a hint, just to throw out another little bit of kind of science that we're not going to use much in Galactic because it's not super relevant to galaxies, but is important to keep in mind. So this is just some data showing that with different globular clusters where they've shown the log of the age after they fit their isochrones in their HR diagram or their color magnitude diagram. So color magnitude is an HR diagram. So just again, so you have seen this as we move forward. Okay. So back into the Shapley-Curtis great debate. Sorry, a little sidetrack there. This is kind of what Shapley was able to come up with as positions of globular clusters around the sky. So what does this tell us about where the sun is in the Milky Way?
So it tells us that we're like right in the middle of the disk, because on the Z axis we're at 0. And it tells us also that we're right in the center of the disk, because again, the X axis is also 0.
So not quite, I like that,
Okay.
but I think in this schematic, 0 is just the position of the sun. So yes, we are at 0, but I think that's how this graph is defined. We can kind of see that we are in the disk because there's an equal number of globular clusters above and below us. So that's kind of the idea that we're using. If there's equal number above or below, are we the center of our disk though? Seeing some shaking heads. Why do we know we're not the center?
I guess if you look at where we are in terms of like the x-axis, we're definitely to the left of most of the globular clusters.
Yeah, so that makes us think that the center is probably somewhere in here at the center of the distribution of the globular clusters. And we know that the sun is about 8.5 kiloparsecs from the center of the Milky Way. So if you kind of look at this, you know, that's about 8.5 kiloparsecs, if just ish. So the center of our Milky Way is going to be kind of at the center of our globular clusters, again, assuming globular clusters are evenly distributed about the sky. Now, in order to come up with this measurement, Shapley had to use the Cepheid period luminosity relationship to find distances to globular clusters. So that was one of the reasons that Curtis argued with this, was that he thought that the Cepheid period luminosity relationship was incorrect, and therefore you couldn't use it to accurately find distances to globular clusters. So this was one of the points that Shapley was maybe more correct on. He still got his size of the Milky Way wrong, because he thought we were about 20 kiloparsecs from the center of the galaxy, and that the Milky Way had a diameter of 100 kiloparsecs. So he got it right that we aren't in the center, but he got his size wrong, which further led him to kind of think that the other spiral nebula must be inside the Milky Way, because the Milky Way is just enormous, which it's big, but it's not quite that big. So another way where he was on the right track, we're doing science correctly. This is kind of how science works. We make the best measurements we can, and we work with what we kind of find that way. So I really like this debate, because I think it is a cool way to think about how science changes over time. Okay. So just as a little overview of kind of what I did hear some discussion of in the earlier breakout rooms, is that neither of them really won. I guess in the reading they kind of talk about how maybe if you ask them later, Curtis would say he won and Shapley would say no one won, so probably Curtis kind of won, but also neither of them were right and neither of them were wrong. So they both got some things right, they both got some things wrong. They were both, based on the information they had, they were working the best they could to make these arguments about what was going on. One point we didn't discuss, so I threw this image in just for fun, was that I think Curtis, sorry. Curtis was also looking at nova and the spiral nebula. So I put in a picture of a supernova in a galaxy, so you can see there's nothing there, and then there is something there. And that's how we find supernova. But they were saying that if we see nova in the Milky Way, we see nova in other spiral nebula, so spiral nebula must be made of similar things to the Milky Way, and therefore island universes, as opposed to something within our own galaxy. So just another argument that got thrown around, but we're still kind of just part of this larger debate that I want to just point out as well. I also want to pause here to point out, I think some people have already answered this, but our day 3 discussion kind of participation points, I wanted to take some time for people to talk about and also answer now. So I'm gonna put you back in your breakout rooms one more time. But what I really want you guys to focus on is kind of the last part of this question. So are there any subjects of debate in astronomy or science in general that you think might, maybe, in 2120, we'll talk about the same way we talk about the Great Debate? So are there things that we think that might spur debates now that we'll look back on and maybe not laugh, but think like, kick them out in 26 seconds. Okay. I think most people are back. I was able to join in on a couple of your guys' talks, which was fun, because I think this is a fun question. Is there anything that anyone's willing to share from their group?
Just quickly, something that's like outside of astronomy, because I'm sure most of us are going to be astronomy focused. Luca, the last universal common ancestor, is like sort of reaching the end of its debate, in that a lot of recent science is pointing more towards there being a singular Luca rather than like 2 or 3. But that's like been a debate in recent history as if there's literally just one, or if there's multiple.
So is that that's for humanity, right? Not all species.
For Earth.
For Earth.
For Earth, it's sort of leaning towards like one single organism that is the last universal common ancestor of all life on Earth.
That's awesome. And that could there's another science thing that could change the way we think about ourselves. Which, yeah, that's really cool. Thanks for sharing. Anyone else?
We talked about being able to figure out what dark matter and dark energy are, be able to maybe have technology that can take pictures of non-EM emitting stuff, potentially. There's a lot that could happen, I guess.
That would be really yeah, well, I mean, it's this kind of thing that we can't imagine because we don't have the mind space to imagining it. I love it. Sweet. Okay. Gonna learn to click the screen one day. Okay. So the thing I wanted to just wrap up was a little discussion of, we'll get more into Sagittarius A-star later, but just if we aren't the center, what is at the center? And the answer to that, we've kind of already talked about it a little bit last week, but we've got a supermassive black hole at the center of our galaxy. And there's just one, we won't, I think we've got 17 minutes and I want to talk about my last question instead. But one thing I think is really cool is that this was an original measurement of the mass of the central black hole, central supermassive black hole. So the Keck group was able to use an infrared telescope to look through all the dust in the galaxy and measure the rotation of a few stars around whatever is in the middle of our galaxy. And so this is the year up here too. So this is a 15-year project that I think is ongoing, where they're really carefully measuring the positions of these stars. And they're able to use the orbits and then Kepler's laws to figure out the mass of what these stars are going around, kind of assuming that the stars are going to be much less massive than the central black hole. So one thing you can see is that this star on the yellow path, I think it's S02, there we go, makes one full orbit in this 15-ish year cycle. So they were able, by measuring these stars for 15 years, you can get one full orbit, you can find a period, you can use angular sizes to get a semi-major axis, and you can figure out the mass of the object in the center. So using Kepler's laws, you can find the mass of the supermassive black hole in our galaxy, which is cool. And it's just kind of amazing to think about a project that took 15 years to complete. It only causes me slight palpitations as a grad student who wants to finish. It's I don't want to be on a 15-year project, but that's why you find a smaller one. So you do part of the project. But just how science is done now, how we've kind of expanded on that. So like I said, we'll talk more about Sagittarius A-star later in the semester, but I just wanted to throw this out there to show a kind of cool measurement that with the data, you guys could all do with the knowledge that you have. Okay, so I wanted to end with one silly question to kind of discuss, so wrap things up. Again, I'll put you guys in your breakout rooms. It's wrong, there was one more time. X-Files has been my go-to pandemic show, so you guys all just got abducted by aliens. And you want to figure out, you need to tell the rest of the class where you are in the Milky Way so they can come rescue you. Or tell someone, maybe tell Andrea. Andrea's gonna come rescue you if you can figure out where you are in the Milky Way. So luckily they didn't, they left you in a fully functional astronomical observatory that has all the equipment you might hope for, because these aliens are just nice, semi-nice, you just don't want to get out. So we need to figure out where we are in the Milky Way. You have any kind of equipment you want. What's your plan? How do we go about figuring out where we are? So let's discuss in your groups are at 10 minutes, and then we'll come back together and I'll again pick on one group to share what they came up with.